Hello everyone. My name is Amir Zaghi, and today I'll walk you through how to measure arterial elastance and end systolic elastance ratio to establish VAC using standard echocardiography and blood pressure data. VAC, or ventricular arterial coupling, quantifies how efficiently the ventricle and the arterial tree interact. I'll start with a physiological background, then a step by step measurement procedure, and finally, clinical examples showing why this ratio adds value beyond ejection fraction. Ventricular arterial coupling is about energy transfer. The LV generates pressure. The arterial system receives stroke volume. Arterial elastance tells us how stiff the arterial system is, while the end-systolic elastance reflects how forcefully the ventricle contracts. When these slopes are balanced, roughly a ratio of 1, the heart works at peak efficiency. If the arteries stiffen or the ventricle weakens, the ratio increases, signaling uncoupling and higher oxygen cost for the same output. The pressure volume loop is one of the most informative ways to understand how the heart works. It shows how pressure in the left ventricle changes as it fills and empties with blood during one heartbeat. On the horizontal axis, you have the left ventricular volume, and on the vertical axis, you have the left ventricular pressure. As the heart beats, the ventricle goes through filling, contraction, ejection, and relaxation. The loop you see represents these four phases, drawn in a counterclockwise manner. Now, the diastolic filling. This is the bottom right part of the loop. The mitral valve is open and blood flows from the left atrium into the left ventricle. Pressure rises only slightly while the volume increases from the end systolic volume to the end diastolic volume. This is the phase at which the ventricle is relaxed. So the pressure increase that you see is mainly on account of the volume that is added to the left ventricle. This curve reflects the diastolic compliance of the ventricle and is represented by the end diastolic pressure volume relationship. A stiff ventricle, like in hypertrophy or diastolic dysfunction, makes this curve shift upward, meaning higher pressures for the same filling volume. Now, once the ventricle is full, the mitral valve closes and pressure begins to rise sharply. But volume doesn't change since both valves are closed. This is the vertical upstroke on the left side of the loop. The muscle fibers start contracting but haven't ejected blood yet. This phase ends when the aortic valve opens, at which point the pressure inside the left ventricle exceeds the aortic pressure. After the aortic valve opens, the ventricle ejects blood into the aorta. This is the top curved part of the loop. At first, pressure continues to rise, then it peaks and slowly falls during late ejection. Volume decreases as blood leaves the heart. The pressure at the end of this phase is called end systolic pressure. The slope of the line connecting the end systolic point of multiple beats under different loading conditions defines this curve. And this curve is equal to the contractility of the left ventricle, and it also constitutes the end-systolic elastance. So a steeper slope means a more contractile ventricle, and a flatter slope means weaker contractility. This point constitutes a key moment, because that is when the ventricle's active pressure generating capacity, which is represented by this curve, and the load imposed by the arteries, which is represented by this curve, are equal. So ejection stops. The aortic valve closes because aortic pressure momentarily exceeds left ventricular pressure. The left ventricular volume is now end-systolic volume. The pressure at this point is the end-systolic pressure. So the crossing of these lines is not arbitrary. It represents the equilibrium point between ventricular contractility and arterial load. The ESPVR and the EA intersection defines the heart's steady state operating point for that beat. It's where the force generating by the left ventricle is exactly balanced by the arterial opposition represented by the arterial elastance. And this position, that is to say, this intersection, represents how well the left ventricle and the arteries are matched. If the arterial elastance increases, for instance, because of stiffer arteries or higher blood pressure, the arterial elastance line becomes steeper. So the intersection point moves up and to the right. And this means higher end-systolic volume, lower stroke volume, reduced stroke work, and lower efficiency. The arterial elastance and the end-systolic elastance ratio would increase, and it constitutes ventriculo-arterial uncoupling. That is to say, the heart is not beating efficiently. On the other hand, if the end-systolic elastance increases on account of stronger contractility, which would mean that the ESPVR curve becomes steeper and the intersection moves up and to the left, it would mean that the area that is marked here as stroke work would become greater, and it would mean lower end-systolic volume, higher stroke volume, and improved efficiency. So the arterial elastance to end-systolic elastance ratio decreases, meaning better coupling. If both end-systolic elastance and arterial elastance increases proportionally, such as during exercise, the intersection may stay roughly in the same place, and the ratio would stay at 1, maintaining efficiency even though absolute pressures and volumes changes. So the energetic consequences of this is that at end systole, there is mechanical energy produced by the left ventricle that can be divided into two. Stroke work, which is the energy used to eject blood, which is marked by the red area here, And then there is the potential energy, which is the elastic energy stored in the myocardial wall at the end of contraction, but which is not used into shifting the volume uh, in the left ventricle into the arteries. Now, example scenarios on the pressure volume diagram could be, for instance, uh, the fact that an increased afterload in terms of hypertension would mean that the arterial elastance line would become steeper. And as said before, it would mean higher level of end-systolic volume, lower level of stroke volume, and a smaller amount of stroke work. That is to say, useful energy. Another scenario is increased contractility. If, let's just say, if you would, for instance, give a heart failure patient dobutamine, and that would cause the SPVR to become steeper, and the intersection would move upwards and to the left. And that would mean less amount of systolic volume, greater amount of stroke volume, and greater amount of stroke work. At first glance, we could take end systolic volume from echo, divide by stroke volume, and call that the ratio. But mathematically, this is just another way of expressing ejection fraction. No new physiological insight. True coupling analysis should tell us whether abnormalities stem from arterial load, ventricular properties, or both. That's why we use the single beat method instead. Chen and colleagues solved the practical problem with a single beat model. It uses measurable parameters from one cardiac cycle and cuff pressures. The estimate of the normalized elastance at the onset of ejection represents the starting point of the systolic elastance curve, and it aims to estimate the end systolic elastance without measuring left ventricular pressure directly. It is based on empirical regression models from invasive data sets. That's to say, patients that have undergone invasive LV pressure volume analysis with conductance catheter and simultaneous echocardiography. With the help of this, we can compute VAC using ejection fraction, the diastolic to systolic pressure ratio, and timing intervals. Modern software or spreadsheets can calculate this automatically once you enter blood pressure, ejection fraction, stroke volume, and timing data. Here are practical echo steps in estimating VAC. Always measure blood pressure close in time to image acquisition. From the left ventricular outflow Doppler, place one marker at QRS onset, another at flow onset to get the pre-ejection period. Then, total systolic time to end of flow. Compute stroke volume as usual, and ejection fraction by Simpson's method. Enter these in an Excel spreadsheet with coefficients for estimated normalized ventricular elastance at the onset of ejection or available software, such as the iElastance by Bertini. It instantly gives arterial elastance, end systolic elastance, and the arterial elastance and end systolic elastance curve. With a bit of practice, this adds only a minute to a routine echo. In conclusion, think of the ratio as an efficiency gauge. When the arterial elastance to end systolic elastance is close to 1, the left ventricle and the arteries are well matched. If the ratio rises above about 1.5, for instance, the ventricle must generate excessive pressure for little volume output, which means that the energy cost increases. Inversely, very low ratios may indicate hypercontractile states, or vasodilation. The beauty of this is that we can now see which side of the system changed, arterial or ventricular. Thank you for listening.